Neil deGrasse Tyson just dropped a cosmic bombshell. What if Neptune isn't the quiet, icy giant we believed, but something far more mysterious and active? We end tonight with the clearest pictures yet of Neptune, the most distant planet in our solar system. We're looking at Neptune's orbit, and it's not following Newton's laws. When Neil deGrasse Tyson made his unexpected revelation about Neptune, it didn't just ripple through the community of astronomers. It shook the very foundations of what many believe to be a well-understood corner of our solar system. Tyson, known for his articulate communication of complex astrophysical phenomena, addressed a packed auditorium during a globally streamed symposium. The world watched in astonishment as he unveiled findings suggesting that Neptune, the icy giant lurking at the fringes of our planetary family, may not be what we have long assumed it to be. For decades, Neptune had been quietly classified as the eighth planet from the Sun, a cold bluish orb of gas and ice orbiting far beyond the familiar warmth of the inner planets. Discovered in 1846 not by direct observation, but through mathematical prediction due to irregularities in Uranus's orbit, Neptune was later confirmed by telescope. Since then, our understanding of Neptune came primarily from a trickle of telescope data and a singular flyby by Voyager 2 in 1989, which provided precious snapshots and surface-level data that framed the planet as a frigid, dynamic world with supersonic winds, massive storms, and a deep blue hue. Yet, much of Neptune remained a mystery. Tyson's disclosure cracked that veil wide open. His announcement centered on recent observations made using data from the James Webb Space Telescope and Earth-based interferometric arrays, revealing anomalies in Neptune's internal composition and behavior that contradict existing models of gas and ice giants. Astronomers detected strange patterns in Neptune's gravitational field, electromagnetic emissions, and thermal output, hinting at a far more volatile and complex interior than previously thought. Instead of the standard layered structure with a rocky core, icy middle, and gaseous outer shell, Neptune appears to house a mosaic of interacting zones, including plasma-like materials and inexplicably warm patches beneath its cloud tops. These warmer regions defy expectations, as Neptune is too far from the Sun to receive significant solar energy, and it lacks moons of sufficient mass to create tidal heating, suggesting an internal energy source. Even more perplexing was Tyson's revelation about Neptune's magnetic field, which, already known to be tilted and offset, is now seen to fluctuate erratically over time. These fluctuations may stem from chemical transformations in exotic ices under immense pressure, producing charged flows that generate a drifting, reshaping magnetic map. Tyson floated a bold idea that Neptune might contain stratified cavities or resonant chambers that influence gravitational and electromagnetic energy in ways we've never seen. Such a planet would defy the standard planetary architecture models and force us to reconsider our understanding of planetary formation and evolution. If Neptune deviates so dramatically from expectations, it could imply that the early solar system's history is far more chaotic than we thought, possibly involving the migration of Neptune and its role in shaping the Kuiper Belt and even expelling a hypothetical fifth gas giant. Tyson also pointed to irregular radio emissions from Neptune, not explained by known interactions with the solar wind, but potentially hinting at exotic quantum-level processes occurring deep within. Adding intrigue, Neptune's atmosphere may contain superionic ices, exotic materials that behave like both solids and liquids, forming slushy, electrified currents that explain its internal heat and magnetic anomalies. These materials, moving in conveyor belt-like flows beneath the surface, could create internal turbulence and explain Neptune's extreme 1,300 miles per hour winds, not as a result of solar input, but from thermal pulses rising from its core. This would make Neptune the first known planet whose weather is internally driven. Tyson noted that if Neptune is fundamentally different, then so too may be the thousands of similarly sized exoplanets, mini-Neptunes, discovered by Kepler and TESS, many of which might now need to be reclassified. He even explored the theoretical idea that Neptune could be a failed star or a transitional object, not quite a planet, not quite a brown dwarf, inhabiting a gray zone between definitions, challenging how we categorize celestial bodies. This redefinition speaks to a broader truth, that planets are far more diverse than we've allowed for, not just in appearance, but in structure and behavior. Tyson's poetic yet revolutionary description of Neptune as a chaotic system in equilibrium captures the essence of these discoveries, a world of internal contradictions stabilized by forces we're only beginning to understand. These insights underscore the critical importance of modern tools like the James Webb Space Telescope, without which these mysteries would remain hidden. The sharper our cosmic lens becomes, the clearer it is that the universe holds far more surprises than we ever imagined. Tyson's announcement is not just about Neptune. It's about the limits of human knowledge, the evolving nature of science, and the thrill of uncovering truths that force us to rewrite what we thought we knew. Neptune, once considered the quiet, distant cousin of Jupiter and Saturn, has now become the most exotic, mysterious, and perhaps misunderstood member of our solar family. A reminder that the universe we inhabit is far stranger, deeper, and more complex than we dared believe. As the implications of Tyson's revelation continue to reverberate, scientists are now urgently prioritizing Neptune as a target for future missions. Proposals are being drafted for orbiters and atmospheric probes that could study the planet up close for extended periods, much like Juno at Jupiter or Cassini at Saturn. The goal is no longer just to photograph Neptune's swirling storms, but to understand the mysterious mechanics that drive them from within. Some researchers have even suggested deploying a network of microprobes designed to enter the atmosphere and transmit data from multiple depths, capturing variations in pressure, temperature, and magnetic flux in real time. There's a growing consensus that Neptune might serve as a natural laboratory, a cosmic pressure cooker revealing how matter behaves under conditions we can't reproduce on Earth. In this sense, Neptune is not merely a planet but a frontier in physics itself. Its strange behaviors may lead to breakthroughs in our understanding of magnetism, fluid dynamics, and quantum chemistry. And as we sharpen our instruments and deepen our curiosity, Neptune reminds us of a simple truth. The more we learn, the more mysterious the cosmos becomes. In that mystery lies the drive that has always propelled human exploration, our eternal desire to know the unknowable. This renewed focus on Neptune has also triggered philosophical debates within the scientific community. If one of our own solar system's planets, visible to our instruments for over a century, can harbor so many secrets, what does that say about the thousands of exoplanets we're only just beginning to detect? For years, planetary models have relied on comparisons, Neptune-like, Earth-like, Jupiter-like. But Tyson's disclosure dismantles the very foundation of those comparisons. What if no two planets are truly alike, even when they appear to be? What if every world is a unique expression of cosmic conditions, shaped by forces we're still struggling to comprehend? These questions are not merely academic. They redefine how we search for life, where we search, and what signatures we consider meaningful. If Neptune's exotic chemistry and energy flows defy known physics, then perhaps other planets do as well. And maybe we've overlooked biosignatures or anomalies elsewhere because we were using the wrong lens, the wrong assumptions. Tyson's insights urge us to throw open the windows of possibility, to imagine worlds not just as variations of Earth, but as entirely new categories of existence. The conversation has also begun spilling beyond academic circles. The public, captivated by the poetic elegance of Tyson's words and the stunning visuals from Webb, has begun to rediscover its curiosity about the cosmos. Social media platforms are ablaze with artists' interpretations of what Neptune might look like beneath its clouds, of what strange weather or surreal magnetic storms could be unfolding in its hidden depths. Educators are incorporating these revelations into classrooms, encouraging students to ask their own questions, to challenge old models, and to see science not as a collection of facts, but as an evolving story still being written. For many, Neptune has become more than just a distant blue. It's a symbol of the unknown still waiting within reach. There's even speculation about whether Neptune's chaotic nature could have implications for spacecraft navigation and future crewed missions to the outer solar system. If the planet emits unexpected radio signals and experiences fluctuating magnetic fields, what effects might these have on communication systems, instrumentation, or propulsion technologies in its vicinity? Could its magnetic anomalies interfere with or even assist space travel in ways we don't yet understand? These are the kinds of questions now being posed at space agencies and research labs across the globe. In the grander scheme, Neptune serves as a mirror, reflecting both the limits of our understanding and the boundless capacity of human curiosity. It reminds us that the solar system is not a static museum of celestial bodies, but a dynamic, unpredictable theater of physical and chemical phenomena. Tyson's announcement, while grounded in data, feels almost mythic in its implications. It draws a line from ancient sky watchers who saw Neptune as a star to modern scientists peering into its soul with quantum sensors. And in doing so, it reinforces one of the most important truths in science, that humility and wonder must go hand in hand. The deeper we look into space, the more we realize how much we don't know, and how much there is still to explore. Hit that subscribe button, share your thoughts below, and let's keep exploring the together. Thanks for watching, and we'll see you in the next.